Hi everyone, today we're going to talk about cell potential, free energy, and equilibrium constant, their relationship. When a reaction is spontaneous, we know that the Gibbs free energy is negative, the cell potential is positive, and the equilibrium constant is greater than 1. For a non-spontaneous reaction, Gibbs free energy is positive, cell potential is negative, and equilibrium constant is less than 1. Now let's derive some kind of formula equation that will relate them together. As we know, Gibbs free energy is the energy available to do work. And cell potential is the potential energy difference in joule per charge in coulomb. So if we then say we cross multiply the cell potential with the charge, that's equal to potential energy difference, which is equal to the work maximum. Now work is done by the system on the surrounding. It's defined as negative. Therefore, there's a negative sign in front of Q E0. The charge of electron is defined by Q, which is the moles of electron times the Faraday's constant. And Faraday's constant is a charge in coulomb carried by 1 mole of electron. Therefore, we can now say the work maximum is minus NF E0, or equal to delta G0, the Gibbs free energy, or equal to minus RT natural log of K, the equilibrium constant. Now we have a relationship between the three terms. As minus NF E0 is equal to minus RT natural log of K, we can then divide both sides by minus NF, and that will then turn into E0 is equal to RT over NF times natural log of K. And remember the earlier relationship where this delta G0 is equal to minus RT natural log of K, and the Gibbs free energy change is also equal to negative NF E0, and the E0 of the cell potential, is equal to then 0.0592 volt over N times log of K. Now how did we get that relationship? Let's examine further. If we plug in the Faraday's constant and we plug in the R and the temperature at 298 K, then log of K is equal to N E0 over 0.0592. And therefore the cell potential is equal to 0.0592, the constant value, over moles of electron times log of K, which is then represented in the diagram above in a three-way relationship. And it will be good for us to remember this three-way relationship. Practice problem number 1. Calculate Gibbs free energy change and equilibrium constant for the galvanic reaction iron and nickel 2 plus ion to form iron 2 plus ion and nickel solid. Now, when we look at the oxidation, it's iron to be oxidized into iron 2 plus, giving out 2 moles of electron. You can define the oxidation potential from your book. And because it's listed as reduction, we flip the equation, change the sign to positive 0.45 volts for the oxidation potential. For the nickel reduction, it is equal to negative 0.23 volts coming out from your book. Now the overall cell potential is the oxidation and the reduction potentials added together, which is 0.22 volts. The Gibbs free energy is minus NF E0, so we insert 2 moles for the electron, Faraday's constant, and then the cell voltage, 0.22 volt, which is also 0.22 joule per coulomb. And it's calculated as negative 4.2 kilojoules. Now the log of K is equal to N E0 over 0.0592. So 2 moles of electron times 0.22 volt or joule per coulomb over 0.0592 is 7.4. Now the equilibrium constant is 2.5 times 10 to the power 7, which is a very large number, indicated equilibrium lies far to the right and the forward reaction will go spontaneously. For the galvanic cell, at standard condition, solution is at 1 molar. So the overall cell potential is 1.10 volt for the zinc and the copper electrodes. Now for non-standard conditions, That means we're changing the concentration from 1 molar. Let's say we're decreasing the zinc ion from 1 molar to 0.1 molar, and this is the product side. And we're increasing the concentration of copper ion from 1 molar to 2 molar, and this is on the reactant side. Because now we don't have enough concentration of the zinc ion on the product side to remain to maintain the equilibrium. Therefore, by Le Chatelier's principle, the forward reaction under non-standard conditions will have a greater tendency to occur, driving the reaction forward to the right, and that will increase the cell potential to be more than 1.10 volts. We also can derive the Nernst equation to calculate cell potential at non-standard conditions. Because delta G gives free energy at non-standard condition is equal to delta G naught at standard condition plus RT natural log of Q, where Q is the quotient. And then we can replace by negative NFE is equal to negative NFE naught plus RT natural log of Q. Now divide the overall equation by the term negative NF. Now we have E, the cell potential at non-standard condition, equal to E naught minus RT over NF natural log of Q. Or simply put, cell potential at non-standard condition is E naught minus 0.0592 over moles of electron times log of Q. Now let's apply Nernst equation to calculate cell potential at non-standard conditions. Using the earlier cell, we have 2 moles of electron, and the quotient is product concentration over reactant concentration, zinc ion over copper ion, which is 0.1 over 2. And now the calculated cell potential is 1.14 volt, which is 0.04 volt more than before, when the conditions have been changed. Cell potential increases as predicted earlier by Le Chatelier's principle. Well, we need to know both ways, the explanation by Le Chatelier and also be able to apply Nernst equation for the calculation. In a concentration cell, the current flow can be driven by a difference in concentration in which the half reactions are the same. Now, under standard condition, we will have copper in the anode as well as copper in the cathode. You can see the oxidation potential and the reduction potential have the same magnitude but opposite in sign, and therefore the overall cell potential will be 0 if we use the same kind of electrode and same kind of solution in the 2 half cells. However, the concentration cell will make use of the changing in the concentration to drive the electron. Let's say we change the concentration of the anode from 1 molar to 0.01 molar, and the concentration of copper ion at the cathode to 2 molar. Now we apply the Nernst equation, and we calculate. Now make sure that you put the dilute solution concentration over the concentrated concentration of the solution. And now we end up with 0.061 volts. And this is the setup in which you have 2 half cells, copper electrode in both anode and cathode. And you have at the anode, it is the dilute concentration, which is 0.01 molar. And at the cathode, we have the more concentrated solution of 2 molar. So the current flow is driven by the difference in the concentration in which the half reactions are the same, and solutions become more concentrated at the anode, but less concentrated at the cathode. How do we apply concentration cells? In the electron flowing from dilute half cell to concentrated cell, increasing this copper 2 plus ion in dilute cell and decreasing concentration of copper 2 plus ion in concentration cell. These are the basis for making of the pH meters. And the nerve cells in our brain that generates a potential across the cell membrane by having different concentration of potassium and sodium ions on the 2 sides of the membrane. Another very popular upcoming cell is the hydrogen fuel cell. It is a device that generates electricity from the redox reaction between hydrogen and oxygen to form water. Now, in the cell, the hydrogen and oxygen are separated and furnished from an external source. We will employ the electron gaining tendency of oxygen and the electron losing tendency of hydrogen to force the electrons to move through an external wire to generate electrical current. The hydrogen flows past the anode, which is a screen coated with platinum catalyst, and undergo oxidation, generating water. The oxygen gas flows past the cathode and undergo reduction and generating 4 moles of hydroxide ion. So the overall reaction is 2 moles of hydrogen reacting with 1 mole of oxygen to form 2 moles of water. And this is very useful to provide heat energy to home, to power cars and consumer electronics, or making drinking water for the astronauts in the space shuttle program. And it will produce much less pollution than the fossil fuel combustion. So here's a diagram showing this hydrogen fuel cell. We have 2 electrodes that are screen coated with platinum catalyst, and we then let the hydrogen flow pass through the anode and generating this hydrogen ion, and let the oxygen flow past through the cathode to generate hydroxide ion. And now we have made water as a result. To summarize what we have learned today, students have learned the qualitative and quantitative relationship between delta G naught, E naught, and K, the equilibrium constant, and the effect of changes in cell concentration on cell potential. The use of Chatellier's principle to reason changes in cell potential. We applied the Nernst equation to calculate cell potential at non-standard conditions. We learned the use of cell concentration differences to drive electron flow and the 2 applications. Finally, we learned the operation and benefits of the hydrogen fuel cell. I hope that you have found this video helpful. If you like it, please give us a like, and I look forward to seeing you in the last part of this electrochemical cell video.